Earthquake! The word alone can paint intense pictures. Giant cracks splitting the ground open, swallowing cars and buildings, the after effects of tsunamis, landslides, and fires. Scary stuff. Some earthquakes are strong enough to be deadly. But of the roughly 1 million detectable quakes that shake our planet every year, most are too mild to rattle even a teacup. So can we predict the bad ones? Hi, I'm Sage, and this is Crash Course Geology. Let's start with a simple question. What's an earthquake? Basically, it's any sudden shaking of the ground caused by waves of energy in the earth. That energy can come from landslides, churning magma, or even meteorite impacts. But usually, an earthquake is the fault of a fault. No, wait, not like the fault in our stars. Faults are underground cracks in Earth's crust where blocks of rock slide and scrape against each other. They can range from thousands of kilometers long to smaller than your fingernail. It's no coincidence that some of the most active earthquake-prone faults sit at the edges of tectonic plates, those massive slabs of crust and bits of upper mantle that surf atop the lower mantle. Tectonic plates are moving all the time, very slowly. This movement puts stress on the rock within Earth's crust. As stress builds, it causes strain, or physical changes to that rock, pushing it, pulling it, or shearing it. Some movement along the fault happens at such tiny, steady creep that there's not enough energy to generate an earthquake. But under great stress, brittle rocks in the crust can bend only so far before something's gotta give. One side of the fault slips against the other, and all that pent-up energy breaks loose. That energy rolls out in waves that jiggles the ground, sometimes drastically changing the surface. That's an earthquake. It's basically rock stress relief. It's good to shake it off sometimes, right, Dwayne? But if most earthquakes are so mild we can't even feel them, how do we know they're happening? For that, we turn to seismologists, geologists who specialize in studying seismic waves, the energy that's unleashed after a slip and breakage on a fault. Seismologists use GPS, radar satellites, and super-sensitive machines called seismographs to detect and analyze these waves as they travel underground. Global networks of these machines record seismic data, which then get shared and studied through a facility called SAGE. Oh, no big deal. Seismologists help us not only better understand how earthquakes happen, but also estimate the risks of one happening. Now, there's more than one type of seismic wave, and some are more dangerous than others. First, there are body waves. Body waves begin from an earthquake's hypocenter or focus, the underground point on a fault where the rock cracks. Then they take a curving path through Earth's insides before reaching the surface. There are two kinds of body waves. A P wave, or primary wave, compresses and squeezes the particles it moves through. It's sort of like what happens when you pull a slinky out on a flat surface from both ends and push on one side. P waves are the speediest waves, so they're the ones that hit first. They're what causes the initial jolt of an earthquake, but they usually aren't very destructive. S waves, on the other hand, are secondary and often quite damaging. They move through the rock more slowly, and they shear particles side to side or up and down, sort of like if I jiggled the slinky like this. Buildings, especially older ones, struggle to withstand the horizontal waggle, sometimes causing them to topple. So those are the body waves, but there's another major type of seismic wave, surface waves, which travel along the, surface. And even though surface waves are the slowest, they can be the most destructive because they produce an undulating pattern with an up and down, back and forth, and side-to-side motion. But not all big earthquakes necessarily produce strong shaking at the surface. Like, seismic waves from an earthquake deep underground largely peter out by the time they reach the surface. Seismic waves are more intense the closer you are to an earthquake's epicenter, the point that's directly above where the fault slipped. The type of ground that seismic waves move through can also affect the intensity of an earthquake. Like in 2011, an earthquake in Virginia was felt up to 600 miles away from its epicenter. But an even stronger earthquake in California was only felt about 250 miles away. The reason? Older rocks. Seismic waves on the US East Coast travel farther because the rocks there are much older than the rocks on the West Coast. The faults in these older rocks have had more time to heal, which lets the waves cross them more effectively and be felt much farther away. Meanwhile, those young whippersnapper rocks out on the West Coast have newer faults, which means seismic waves don't spread as effectively. When it comes to measuring earthquakes, scientists use a system called moment magnitude, or MW, an update to the more familiar Richter scale. Moment magnitude describes the absolute energy released during an earthquake. It's reached through a combination of seismic data and the physical shifts in the land that happened during an earthquake. Usually this is just referred to as magnitude, or how much energy was released in general. The bigger the area of a fault that breaks, the bigger the magnitude. Often when a big earthquake first makes the news, its magnitude is just a rough estimate. A truly accurate measurement can take days to calculate. Even though it might not sound like it at first, the difference between just one order of magnitude can be striking. Magnitude was measured on a logarithmic scale, so each whole number represents a 10-fold jump in energy. Let's put that in spaghetti terms, a la my favorite earthquake geologist, Dr. Wendy Bohan. Just go with me. Let's say a 4.0 magnitude earthquake is equivalent to the energy it takes to snap one noodle. Don't get mad at me, Italians. It's for science. If that's the case, then a 5.0 magnitude event would be like snapping 32 noodles. And a 6.0 magnitude earthquake would be like snapping roughly 1,000 noodles. Yeah, I don't think I can do that. I'm just gonna clean this up. So the higher up you go on the scale, even by just a point or two, the more drastic the consequences. Consider the 2009 earthquake that struck the city of L'Aquila, Italy. It was eventually recorded as a 6.2 on the moment magnitude scale. The quake brought 20,000 buildings crashing to the ground, killing over 300 people, injuring 1,500, and leaving 65,000 houseless. It left a lot of people asking, was this damage preventable? For weeks before the quake, the people of L'Aquila felt smaller tremors in the city, but a government commission tasked with monitoring earthquake risk reassured the public that the shaking was normal, and a bigger event was unlikely. Sadly, those tremors turned out to be foreshocks, smaller earthquakes that sometimes precede a serious event. In light of the tragedy, that government official and 6 scientists were accused of giving, quote, inexact, incomplete, and contradictory information that downplayed the true risks. 3 years after the earthquake, an Italian court convicted them of manslaughter for not properly warning the public of the danger. But here's the thing. We can't know if something's a foreshock until after the bigger earthquake happens. It's common for small earthquakes not to lead up to a worse event. And it's possible for a strong earthquake to happen with no foreshocks preceding it. So can we tell when a tremor is nothing to worry about? And when it's the lead up to something more dangerous? And how do seismologists even estimate earthquake risk? Well, it's nuanced. You see, prediction has a very specific meaning in earthquake speak. To predict an earthquake means you've pinned down the exact time, date, location, and severity. No one has ever predicted an earthquake. Not once. In the words of the U.S. Geological Survey, we do not know how, and we do not expect to know how any time in the foreseeable future. In other words, you can't just schedule an earthquake reminder in your Google Calendar. What scientists can do is forecast earthquake risk in a certain area. It's a lot like a weather report. A meteorologist can't tell you if or when it will rain, only that there might be rain somewhere during a certain period. Forecasts deal in probability. It's an estimate of the long-term odds of an earthquake happening in a specific fault sometime in the future based on how much time has passed between big earthquakes in a particular spot. Which is why gathering and analyzing seismic data is so important. They're what forecasts are based on. They're also based on literally digging into the past for evidence of shaken up sediment in the rock record, which tells us about the cadence of ancient earthquakes. There's always some uncertainty in forecasting, much like what happened with the L'Aquila earthquake. Over 5,000 members of the scientific community signed an open letter to Italy's president calling it manifestly unfair to bring criminal charges against scientists for not acting on information that, quote, the international scientific community would consider inadequate for issuing a warning. In light of those facts, the charges against the scientists were dropped in 2014. And though we'll probably never have an earthquake crystal ball, there are ways we can prepare. Places like Japan, Mexico, and California have developed early warning systems that notify people at the first signs of seismic waves, giving even a few precious seconds to get to a safer spot before the big shock hits. Many areas require new buildings to be constructed with earthquake-resistant techniques and materials, so they're less likely to collapse. And because earthquakes can happen anywhere, we can all personally prepare by getting familiar with the seismic risk where we live, and learning what to do if an earthquake ever affects our area. Earthquakes can happen anywhere on Earth, at any time, and unfortunately, we have no way of predicting exactly when or where. But by studying and tracking seismic data, scientists continue to refine forecasts, better assess the risks, and even research how to prevent and protect us from the most damaging shocks. Next time, we'll learn more about earthquake preparedness. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed in our studio in Indianapolis, Indiana. It was made with the help of all these nice people. If you want to help keep Crash Course free, for everyone, forever, you can join our community on Patreon.